Hi guys, welcome to this
Collab
collab video. In this video, we're going to be talking about atomic structure. So the first thing we need to talk about is electromagnetic radiation. So basically there are different wavelengths of light. So we have the different spectrums. So there's UV, visible light, which obviously is like what we see, infrared, microwaves, and there's radio waves, etc. There's a few others. So wavelength is represented by this symbol here called lambda, and it means the length between two successive crests. So you don't really need to know that, but essentially it's like it determines what category it falls into. And frequency is this symbol here, and it's the number of cycles per second that passes a certain point in space. So that's also has to do with this equation here. So the speed is equal to the frequency times the wavelength. So we're going to get a little bit more into frequency down here. This is a picture that you had in your Renee McCormick notes if you looked at those yet. And this is really helpful because you know that when wavelength is increasing like this, we have the different spectrums of light. So we have gamma rays, X-rays, ultraviolet, and this is the small boundary of visible light that we see, infrared, microwaves, and radio waves. So you kind of have to know, this isn't too important on tests or on the AP test, but if you can, try to memorize generally what wavelength it has to be in order for that category to be in place. And then you kind of should know a little bit about trends. So this is derived from the equations that we have. So when wavelength is increasing, frequency is decreasing, and wavelength increases, energy of the photon decreases. So energy of the photon. So we can measure the energy of any photon using Einstein's equation. So E is equal to hf. So h is Planck's constant. So that's 6.63 times 10 to the negative 34 joules times seconds. And we have frequency here. We talked about that a little bit on the first slide. And frequency is equal to c over lambda, and c is the speed of light. So c is also a constant 3 times 10 to the 8th. So if you needed to manipulate this equation, if you don't have frequency, you can just plug in c over lambda and solve for the energy of the photon. So different types of light spectrum. So we have, this isn't too important, but it's a good thing to know. So the emission spectrum, it's the spectrum of bright lines, bands, or continuous radiation that is provided by a specific emitting substance. So essentially it loses energy and returns to its ground state, or light is given off by an excited electron. And excited electrons become really important, I think, in the next chapter. Absorption spectrum, so graph or display relating how a substance absorbs electromagnetic radiation as a function of wavelength. Line spectrum is isolate a thin beam by passing through a slit, and then a prism or a diffraction, which sorts into discrete frequencies or lines. So this is also something that is a little important. You probably went over this a little bit already, but photoelectron spectroscopy graphs, otherwise known as PES graphs. So essentially, you would get something like this, and you would have to determine what element it is. So you determine this by basically higher binding energy means that the electrons are closer to the nucleus. So the binding energy is here on the x-axis. So when you have a higher binding energy, that means that those electrons in that shell are the closest to the nucleus. So there's a stronger electromagnetic pull. And it's easier to remove electrons that are farther away from the nucleus. So, for example, electrons that are out here on the graph would be much easier to remove. The height of the peaks represents what element it helps you determine what element it is. So the first peak here has a height of 2. So 1, 2. The intensity is, for example, if you've already gone over ground state configuration, electron configuration, you know that the first thing you usually write is 1s2. So this peak would represent 1s2 because it's really hard to remove those first 2 electrons that are the closest to the nucleus because there's such a strong pull. And then we have 2s2 here, which looks pretty similar, except it's much easier to remove. And then we have 2p6, which is a higher peak, so that represents the 6 in the non-metal category, and so on. So that can help you determine what element is on the PES graph.
Okay, so now we're going to talk about some atomic models. So the first one is the Bohr model. That is a model that only works for the hydrogen atom. And Niels Bohr, who invented this model, he believed that the electrons orbit around the nucleus as like planets orbit around the sun. Except that doesn't, after like looking at other atoms other than hydrogen, he found that that doesn't really work for the other atoms, and he believed that when an electron absorbed energy, it goes to an excited state and goes up in energy level, which is actually pretty correct. Okay, so now we're going to go to the next slide and talk about the quantum mechanical model. So this is the most current model of the atom. It was invented by Louis de Broglie, and he came up with the idea that electrons should be treated as waves, not particles. So a major flaw in the Bohr model was that electrons were seen as particles, and they were orbiting the planet or orbiting the nucleus. But instead, in the quantum mechanical model, we can see that the electrons are not actually orbiting the nucleus in a clear path. They're sort of in a cloud, and you cannot find the exact position at any instant because they're more like waves, and you can only find the probability of finding an electron in a particular location, which is sort of an important topic because you never actually know where an electron is, but you can find like that it will be like a 90% chance of it being in a certain location. So, okay, so now we're going to talk about quantum numbers. So there are 4 quantum numbers. So the first one is n, which is the principal energy level, and that goes from 1 to infinity, and it indicates the most probable distance from the nucleus. Then there's L, which is angular momentum, and L is no larger than n-1. And if you look in these tables here, you can sort of see that L corresponds to the subshells. So like if L equals 0, that means it's an S subshell. L equals 1, that's a P subshell, and so on. And then M sub L is a magnetic quantum number, and it describes the orientation of an orbital in a given subshell, and it ranges from negative L to L. So as you can see, if we had this electron orbital diagram here, this would probably be for a P subshell. So this would be -1 this first block, then 0, then +1, and it just goes like that. So there's always 0 in the middle. So yeah. And then M sub S is spin, and that accounts for the reaction of the electrons in a magnetic field. So M sub S can be -1/2 or +1/2. So we're just going to go over some important terms that have to do with magnetism. So I've seen these on a test before, and basically nobody knew what they meant. So diamagnetic means it's not magnetic, and it's actually repelled by a magnetic field, and that occurs when all electrons are paired. Next, there's paramagnetic, which means that it's attracted to a magnetic field, so it has one or more unpaired electrons. However, it loses magnetism when it's removed from a magnetic field. And finally, ferromagnetic is something that retains magnetism upon introduction to and removal from a magnetic field. So in other words, it's always magnetic, no matter if it's in a magnetic field or not. Now we're going to talk about 2 important rules and principles. So the Pauli exclusion principle. So that is that no 2 electrons can have the same set of 4 quantum numbers. Therefore, no atomic orbital can contain more than 2 electrons, and for 2 electrons to occupy the same orbital, they must have opposite spins. So as you can see in this diagram, in this first one right here in the 2s, where you can see the red X, those 2 electrons would have the same 4 quantum numbers, which the Pauli exclusion principle says that cannot happen, which makes sense because you cannot have 2 electrons in an orbital that have the same spin. So that's the Pauli exclusion principle. And then Hund's rule is that the most stable arrangement of electrons is with the maximum number of unpaired electrons, because that minimizes electron-electron repulsions. So electrons are going to fill in one by one before they start pairing. So in the one that says correct, you can see that they've filled in one by one and not paired because they don't need to. However, in this second one that's incorrect, they pair up first, which Hund's rule says is incorrect because that will make more electron-electron repulsions. That's all. Thank you. Hope you enjoyed this collab.